Hello, welcome back to this series of videos where I'm studying the white paper. Today, in this final video, I'm not sure if it's the last one, but it's one of the last videos. I will read and discuss the chapter 11, calculations. Then I will read and discuss conclusions. Okay, so let's see one thing. We already have been through these, and I'm curious where these other nodes are being used. Just to have an idea. Okay, so node 11 is here. And the 7th, which is Adam's back paper, and oh no, the 7th is about Merkle tree techniques. Okay. Therefore, in chapter 11, we have a lot of text, as you can see. There are these 3 paragraphs, and then some formulas, definitions, other 3 paragraphs, 4 paragraphs, other formulas. So there are 7 paragraphs in chapter 11 and a lot of the definitions and formulas. Okay, so let's start with the first one, which says we consider the scenario of an attacker trying to generate an alternate chain faster than the honest chain. Even if this is accomplished, it does not throw the system open to arbitrary changes, such as creating value out of thin air or taking money that never belonged to the attacker. Nodes are not going to accept an invalid transaction as payment, and honest nodes will never accept a block containing them. An attacker can only try to change one of his own transactions to take back money he recently spent. The race between honest chain and an attacker chain can be characterized as a binomial random walk. The success event is the honest chain being extended by 1 block, increasing its lead by +1, and the failure event is the attacker's chain being extended by 1 block, reducing the gap by -1. The probability of an attacker catching up from a given deficit is analogous to a gambler's ruin problem. Suppose a gambler with unlimited credit starts at a deficit and plays potentially an infinite number of trials to try to reach break-even. We can calculate the probability he ever reaches break-even, or that an attacker ever catches up with the honest chain, as follows. So here there's the mention of Note A, Feller, an introduction to probability theory and its applications. Okay, so probability and honest node finds the next block. This is probability P. Probability Q is that the attacker finds the next block, and QZ is the probability the attacker will ever catch up from Z blocks behind. So the attacker starts his series of tries to find the next block when he has a disadvantage of Z blocks. Therefore, here we have a binomial distribution, which implies that QZ is equal to this system. So QZ is 1 if the probability that a honest node finds the next block is smaller than Q. So if some way the attacker has higher probabilities, it's sure that the attacker will ever catch from the Z blocks behind. Instead, if the probability that honest node find the next block is higher than Q, then we will have QZ being equal to this fraction. So Q on P elevated to Z. So given our assumption that P is measured than Q, the probability drops exponentially as the number of blocks the attacker has to catch up with increases. So let's imagine that, you know, these numbers are all numbers smaller than 1. Therefore, when we divide Q divided P, they're already smaller than 1. And this will this result will be even smaller than 1. And smaller numbers smaller than 1 elevated to a huge number normally will increase the number of decimals of zeros. You can have a look at, for example, let's go on Google and let's ask how much is 2 divided 3. 2 divided 3 is this number here. But if we put, for example, 0.2 divided 0.3, it will be this number here. If we elevate this to, for example, 2, it's shortening the number. So if we elevate to 5, it will be even smaller, so on. Therefore, the bigger is Z, the less probabilities the attacker will ever catch. The smaller is the probability that the attacker will ever catch up from Z blocks behind. And this statement is based on our assumption here in the proof of work chapter. We say that the majority decision is represented by the longest chain, which has the greatest proof of work effort invested in it. If a majority of CPU power is controlled by honest nodes, the honest chain will grow the fastest and outpace any competing chains. So this piece of text here is coded in chapter 11 in this way. So this is the mathematical representation of that piece of chapter 4. Therefore, now with the odds against him, if he doesn't make a lucky lunge forward early on, his chances become vanishingly small as he falls further behind. We now consider how long the recipient of a new transaction needs to wait before being sufficiently certain that the sender can't change the transaction. So this statement here is talking about this consideration. Which says that an attacker can only try to change one of his own transactions to take back money he recently spent. And this means that if the number of set blocks that have been built on top of that block containing his last transaction, if the number of those blocks on top of it are too small, the receiver of the money, it can't be sufficiently certain that the sender can't change the transaction. So we assume the sender is an attacker who wants to make the recipient believe he paid him for a while, then switch it to pay back to himself after some time has passed. The receiver will be alerted when that happens, but the sender hopes it will be too late. So the receiver generates a new key pair and gives the public key to the sender shortly before signing. Okay, so this is something we discussed. Every time you receive UTXO from someone, you need to generate a new key pair. Sorry, not a new key pair, but an address. This prevents the sender from preparing a chain of blocks ahead of time by working on it continuously until he is lucky enough to get far enough ahead, then executing the transaction at that moment. So yeah, this generating the new address, the new public key, allows also to not give the attacker time to build on existing information a plausible transaction. Once the transaction is sent, the dishonest sender starts working in secret on a parallel chain containing an alternate version of his transaction. The recipient waits until the transaction has been added to a block and Z blocks have been linked after it. He doesn't know the exact amount of progress the attacker has made, but assuming the honest blocks took the average expected time per block, the attacker's potential progress will be a Poisson distribution with expected value. Lambda equals set Q on P. So a Poisson distribution is a distribution where the events in each moment have the same probability to happen independently of the previous events. Therefore, in this type of distribution, the probability lambda is, the expected value of the event will be equal to the probabilities in this fraction multiplied set. So this is the probability. So to get the probability the attacker could still catch up now, we multiply the Poisson density for each amount of progress he could have made by the probability he could catch up from that point. So this is another way to calculate probabilities in Poisson distribution. So here we have this definition of QZ in a binomial distribution. With the other assumption we've made, we have this other definition. So the probability he could catch up from that point on is another deterministic distribution, which has this aspect. So these are coefficients where lambda has been calculated here and is typical of that distribution we're observing in that moment. K, I don't remember, I don't recall. It should be the number of K, I think it's the number of if that is the number of blocks we need to catch up, sorry, lambda is, yeah, z is the number of blocks we need to catch up. K, I don't remember, it's something we subtract to z if k is smaller than z. And if k is measured than z, then this factor is 1. Therefore, we will have e, which is 2.18, right? Oh no, so it's 271. It's a mathematical constant called Euler numbers. Let's see in English. Euler's number. Okay. So this stuff here, rearranged to avoid summing the infinite tail of the distribution, blah blah blah. Yeah, because here we are considering the distribution to infinite. We can, you know, utilize this stuff here and rewrite all this formula in this way. Okay, so converting to C code, double attack success probability. Okay, so here is just reporting all these characteristics of our mathematical problem. Running some results, we can see the probability drop off exponentially with Z. Solving for p less than 0.1%. Okay, so here we had a lot of mathematical considerations saying that, basically in few words, the most blocks have already been created in the chain, the more the less is probable that the attacker will be able to catch up. Therefore, when you receive a transaction, you will need to wait for not only confirmations, but for some blocks to be built on it. Maybe, let's see here. So if we have, for example, this probability for the attacker to catch up. No, sorry, this is the probability that he can resolve the next block. Then if 0 blocks have been added up, if he can resolve the next block, this means that he for sure will be able to catch up. So when receiving a transaction from someone, you will need to wait at least, if you want to reduce the probability to less than 2 decimals, you will need to wait 4 blocks. In 5 blocks, you already reduced it in less than 3 decimals, and 7 blocks is where the probability that the guy can catch up and reverse the payment is less than 4 decimals. At 10 blocks past his transaction, these become less than 5 decimals. So let's see that even increasing by 3 times his probability of resolving the next block, which is basically his computational power. So this is a huge number, you know, nobody has these numbers nowadays. I mean, maybe someone has a lot of computational power, but they do not arrive at this probability of catching up and resolving the next block. Even with such a high probability, the numbers are still in favor. Like after 5 blocks, you have, a good probability that he can catch up, but after 20 blocks, which is 20 per 10 is like 200 minutes, it's like 3 hours. After 3 hours, there's this little probability, less than 2 decimals, that he can catch up and reverse the transaction. After 25 blocks, which is 240 divided by 60, which would be by 6 is 4. So after 4 hours, with such a high computational power, they have less than 3 decimals probability to catch up and reverse the transaction, and so on. So solving for p less than 0.1, even having such a low probability that the honest will resolve the next block, and even having such a probability that this guy can resolve the next block, we still have a number of blocks which will imply that the attacker cannot reverse anymore his transaction. Therefore, in such cases, you just need to wait. Okay, so what happens is that we have proposed, here we have the conclusions already, and this chapter is already, I will say, a way to take conclusions on this paper, on this system that has been proposed. And the author says, we have proposed a system for electronic transactions without relying on trust. We started with the usual framework of coins made from digital signatures, which provides strong control of ownership, but is incomplete without a way to prevent double spending. To solve this, we proposed a peer-to-peer network using proof of work to record a public history of transactions that quickly becomes computationally impractical for an attacker to change if honest nodes control a majority of CPU power. The network is robust in its unstructured simplicity. Nodes work all at once with little coordination. They do not need to be identified, since messages are not routed to any particular place and only need to be delivered on a best effort basis. Nodes can leave and rejoin the network at will, accepting the proof of work chain as a proof of what happened while they were gone. They vote with their CPU power, expressing their acceptance of valid blocks by working on extending them, and rejecting invalid blocks by refusing to work on them. So this statement is important because if a miner wants to use his computational power to create invalid blocks, they will be refused. So all the computational power this miner used will be thrown in a bin it will be just dissipated, as the network will not accept it, as this invalid block is not allowing the other nodes to complete the protocol. Any needed rules and incentives can be enforced with this consensus mechanism. Any needed rules and incentives can be enforced with this consensus mechanism. Wow, what a statement to close. So, ladies and gentlemen, 8 pages. This took me 9 videos. I will not check this. I may check it just for curiosity, but it looks like just probability theory paper, which is interesting, of course, in general, but in this case, I'm focusing on material which is more like cypherpunk or cryptography related. And okay, I loved going through this document. It's rich, well done, inspiring, and now that I finished discussing it, I'm wondering if 15 years after its publication, nearly 15 or more than 15 years, I'm not sure, but after such a long time, I'm curious if someone replied to this paper, so we know that people use this technology, and this technology nowadays is really important. It reached high levels of attention. Our society is pervaded by it. So even if someone did not invest on it, it's still conditioning their life. And other than thinking of it as an investment, it's conditioning society in many other ways, not only financially. My interest is to discuss mainly the social impact of this network. The financial impact, I will say, it's kind of boring, in the sense that, of course, it's impossible to not analyze it when going to analyze the social impact, as, of course, the speculation is maybe the first factor that attracted huge masses of people. But there's more to it, and I already had the pleasure to explore some ideas which consider how this protocol is changing the behavior of people in society. And I would like to explore this social impact, to understand its effects, checking both the academic thinking and series of publications on it. So I will search for people that discussed this network, maybe proposing improvements. Therefore, from here comes also the need for a technical exploration, which cannot be ignored. Technical aspects are strictly related to social aspects, in the sense that they have this feedback relation in which they influence each other. For example, one other really cool thing that may be explored is all that huge mass of discussions around how to change the protocol. all the changes that have been proposed and accepted by the network during the years are really interesting. They are shaping the network, they are shaping the way the network influences our society, and there's continuously people proposing for changes. Also, there's continuously people proposing for new uses of it without changing the network. It's more about proposing new ways of using the transactions. So instead of using it as a purely financial transaction ledger, there's a lot of people, for example, proposing to use it more as a time ledger, a time chain. This is how someone calls it, and it's interesting. It's interesting because there's a lot of people participating to the discussion, and yeah, it's a huge universe which is colliding with the real life universe. They are getting merged, and it's interesting to understand it, and to provide myself and the others with good ideas on how to use it in a good way. And also it's interesting to explore what may be a bad scenario in which this network in some way augments inequality. Yeah, this is my principal concern, I would say. And yeah, that's it. I'm happy that this first exploration of this paper ended now. I'm happy to finish things. I have this passion for concluding, and let's see what will be the next chapter, the next move. I will decide it shortly and start a new series of videos. You can be sure that I will continue this in some way, or with a more technical analysis of some aspects. For example, I'm thinking about Andreas Antonopoulos' books, which I already read, and it would be nice to take some parts of it and discuss that other beautiful work which Andreas Antonopoulos gifted the whole community with. So yeah, this work will continue, and I'm happy to contribute. This series of videos which I started has the main goal of allowing me to contribute to the network, contribute intellectually and also technically. I would love to be able to discuss issues in the various contexts where people is discussing them, contributing to the discussion in a positive way, in a constructive way. I would love to make this network work for people and create more equality. I would love to allow people to discover it, to be able to discuss and comprehend it, so more people thinks about it, more people discuss about it, more people participate to this network actively or just intellectually. The more people discuss it, the more participants there are, the higher the quality of the output will be. Therefore, thank you for consuming these videos. It was nice to create them, and see you in the next video.